Assalamualaikum warahmatullahi wabarakatuh. My name is Maisarah Binti Daud and my Matric number is 1727452. Today I will be presenting my final year project which titled Computer Simulation of Rainfall Runoff Process for Sungai PUSU, and my project is being supervised by Professor Dr. Abdullah Mamun. Now let's proceed to the introduction. Throughout the years, IIUM compound has been subjected to flood, which causing road closures due to high water levels, which might lead to negative outcomes such as infrastructure breakdown and more if no precaution are taken. For example, here we can see the hotspot of flooding areas in IIUM, Ghazali Walk, Mahalla Uthman, Kaed, and also MSC parking. So, in order to overcome the said problem, this project is subjected to few objectives, which are to set up SWMM model creating the watershed of interest, which in this case will be taking place in Sungai PUSU. Also, the objective is to calibrate and validate the rainfall runoff model using recorded data, which is former rainfall event and flow data. Other than that, it is to design the ponds and outlet sizes to reduce the flood levels in the river within Gombak campus. Included in the method are setting up a model by drawing system layout comprises objects such as subcatchment, rain gauge, junction, divider, storage unit, conduit, and infiltration method. Next, parameters are of the concerned objects are set such as rain format, rain unit, inverse elevation, area with values of N pervious and impervious, depression storage for pervious, depression storage for impervious, land uses, shape of conduit, length, roughness, and the culvert code. Simulation outputs are calibrated and validated to get the most desirable result when compared to the recorded data that obtained from secondary sources. Flood resilience of Sungai PUSU was done by adjusting the size of ponds and outlets so that it can accommodate stream flow accordingly without flooding. Now let's move on to the result produced from this project. In this part, it divided into two subtopics, which are hydrological analysis and hydraulic analysis. Starting with hydrology outcome is the subcatchment delineation. It has been delineated based on digital elevation model, drainage system, and road network in the study area. The Sungai PUSU watershed is split into roughly about 76 subcatchment into this study. Maximum overland flow is the length of the flow channel from outlet to the most remote drainage point in the subcatchment, which in this case is near to gate 2 of IIUM Gombak campus. And the width of a subcatchment is the average of maximum overland flow. The surface area of the subcatchment is divided into two types, pervious or impervious. Next is how do the data were collected to be used in the simulation. First, subcatchment characteristics were determined by observation. Site inspection and Google Earth were also used to acquire topographic data such as elevation and land use in the research region. And then site investigation again was used to determine the river characteristics. As shown, this is the delineated Sungai PUSU subcatchment. Meanwhile, this is the subcatchment properties used in the modeling. The value of N roughness and depression storage depth for both pervious and impervious. Also, the Harton parameters. As shown, this is the established final model for Sungai PUSU subcatchment in stormwater management model, which comprising the river network such as junctions, conduits, and storage units. For the rainfall and stream flow data, the rainfall was collected from rainfall station under management of the Department of Irrigation and Drainage. The station ID is 321-7001 and 321-7004. The stream flow data was collected from ISCO water level and velocity sensors that were put in Sungai PUSU at the IIUM Gombak campus second gate to monitor the stream flow. Single storm events occurred on 4th, 5th, 15th, and 20 November were used in the model. Next is the calculation of IDF curve, which is using the guideline provided by MASMA 2nd edition August 2012. The fitting constant depending on the rain gauge location. And it is taken from this table, which we are using the mean, of station ID 3217001 and 3217004, since both of them have high chances in influencing observed value because of the location of both located upstream of the catchment. And this is the design rainfall intensities for various ARIs. Due to IUM is an industrial commercial building, the annual recurrence interval chosen is 50 years. And the time of concentration decided was 1 hour, which the process of obtaining it will be explained soon. This is the IDF curve resulted from IDF calculation previously. So for the last part, for hydrological analysis, is determining the time of concentration for Sungai PUSU catchment. To obtain the critical storm duration, a hypothetical uniform rainfall of 5 mm for each 5-minute interval, the duration for 6 hours, was applied. And as you can see, the first 1 hour, the hydrograph peak becomes flat, which indicate the whole catchment is contributing flow, or also means the greatest stress occurred on the drainage system, including the maximum surcharge and system outflow. So in comparison of hydrographs, due to various storm durations were also done. Various storm durations of 1 hour, 1.5 hours and 2 hours were done in order to find the maximum peak flow. As shown, rainfall of duration 1 hour generate maximum peak flow. So now for the calibration part. Field or observed data were utilized in this work to calibrate the model at specific period by modifying model parameter values until a satisfactory correlation was reached. And then the model was calibrated against the observed water level. In this investigation, the observed water level nearly matches the estimated water level as will be shown in the graph. This is the storm event of 4th November 2015. This is the storm event for 5th November 2015. This is the storm event for 16th November 2015. And lastly is the storm event of 20 November 2015. So for the third objective of this project is the flood mitigation measures, and the stream flow intake and outflow of the pond as well as the maximum water head in the pond are simulated with design rainfall of 50 annual recurrence interval for flood improvement resilience, like we already discussed earlier. So for the improvement options, there are there are three that we are considering to apply so that the flood will be the possibility of flood to happen will be reduced. The first option is to examine in lowering the likelihood of a flood is to expand an existing inlet or outlet to enhance the amount of water available to keep moving without becoming stagnant in the pond for too long. The second option for improving flood resilience is to install extra pond outlet to allow more water contained in the pond to flow downstream at the same time, while maintaining the pond's head level without spilling more water. And the third enhancement option was to increase the pond's capacity to store water, which included increasing the pond's maximum depth and size. So as you can see, this is for pond 1. From the top left graph, as you can see, there is a flat line in the pond head which indicates the flood occur. These are the improvements that we have done in order to enable, in order for the pond to not reach the maximum depth. So from the existing structure, it only has one circular outlet and has 3 meter depth. And for the pond dimension, the maximum depth of water allowed is 3 meter, and the area is 24,145 meters square. And we improve it by adding one more circular outlet, and for both circular outlet we increase the size to 4 meter depth, and the pond dimension will also increase the depth by 1 meter and increase the area until it's 30,431 meter cube. And then after the improvement, the water can flow again. in the graph. And then for the pond 3, pond 5 and pond 6, we only apply 2 options, which we add another 1 extra outlet, and also we increase the depth for both circular outlet. So this is the result for pond 3, and this is the result for pond 5. When we do the improvement, it increases the water depth that is allowed in the pond. And also this is the pond 6, which pond 6 is located near to MSC parking. And lastly, for the pond 7, which is located at the junction next to the roundabout, the existing structure of it has 1 open rectangular inlet. The dimension of the inlet is it has maximum depth of 3 meter, and the bottom width of the inlet is 7 meter. But as option to reduce the flood level, we increase the depth and the bottom width. We increase the both maximum depth of inlet and also the outlet. So for the pond 7 only, we didn't add extra culvert. We didn't add extra outlet, but we increase the dimension of inlet and outlet of pond 7 from maximum depth 3 meter, bottom width 7 meter. It has a rectangular outlet and inlet. We improve it to 4 meter depth and 8 meter bottom width. So after the improvement, the flood is no longer happening. Conclusion and recommendation. So this is the last part. In the conclusion, it was discovered that percent imperviousness, percent zero imperviousness, and the pressure storage pervious are the most critical model parameters. That is, a little change in imperviousness, depression storage or depression storage depth will have a considerable impact on the simulated runoff and peak flow. And also, depression storage for pervious is more sensitive to the model than the other 2 factors. It was also shown that decreasing rather than increasing depression storage factors, it has greater impact on peak runoff. It indicates that a little drop in depression storage depth will result in a significant increase of peak runoff. Meanwhile, the recommendation for future studies are the future research in the field of stormwater modeling should take into account the difficulties of data collection and model calibration, because there were a lot of uncertainty that need to be considered in stormwater runoff modeling. For example, input uncertainties, parameters uncertainties, and model structural uncertainties. As a result, further research might resolve this concern. Furthermore, land cover in urban catchment is not uniform, which has an impact on physical processes. Lastly, the usage of stormwater management model in simulating actual event is very recommended, considering the abilities and functions that are offered within regarding water quantity. So that's all from me. Thank you so much.